Welcome back to Inside Factory Produce. Today, we are crossing the threshold into the most demanding realm of modern manufacturing, aerospace engineering. We are peeling back the metal skin of a commercial jetliner to look directly into the beating, fiery heart of a jet engine. At the center of this titanic machine sits the high-pressure turbine blade. This component operates in an environment hotter than the melting point of its own metal, subjected to centrifugal forces that try to tear it apart with every rotation. To survive, it cannot be made like ordinary metal. It must be forged as a single, perfect crystal. The journey of this aerospace masterpiece begins not with raw steel, but with a delicate, translucent blue wax. Watch as a high-precision robotic arm injects industrial wax into a mirrored steel die under heavy pressure. When the die splits open, it reveals a flawless, smooth wax pattern of the turbine blade. Every line, every curvature must be absolutely immaculate. A technician wearing white silk gloves lifts the pattern, inspecting it under harsh laboratory lights. Even the microscopic trailing edges are scrutinized under a stereo microscope. These individual wax blades are then carefully welded by hand to a central runner, creating a complex structure known as a wax tree. Inside this dust-free cleanroom, the blue tree looks like a high-tech sculpture. But this wax is just a placeholder, a phantom shape that will soon dictate the flow of molten superalloys. We are witnessing the first step in forging the fire threads that hold our skies together. Part 2. The Ceramic Shell and the Vacuum Inferno, shots 11 to 30. 120 to 320. The wax tree must now be transformed into a mold capable of withstanding volcanic temperatures. A multi-axis robot dips the assembly into a thick, bone-white ceramic slurry. The tree rotates slowly, ensuring the liquid coats every internal curve and labyrinth passage. Immediately after, it is moved over a fluidized bed, where a heavy rain of fine zircon sand showers the wet surface. These sharp sand grains embed themselves into the slurry, creating a rugged, concrete-like layer. This process of dipping and stuccoing is repeated 7 times over several days, creating a thick ceramic shell around the wax. Once dry, the entire assembly is pushed into a steam autoclave. Under intense pressure, the internal wax melts completely and pours out of the bottom vents, leaving behind a completely hollow, empty ceramic cavity. This hollow mold is then baked in a preheating kiln at 1000 degrees Celsius to lock its crystalline structure. Now, the metallurgy begins. We introduce a heavy ingot of a nickel-based superalloy, a proprietary blend containing rare elements like rhenium and ruthenium. This metal is placed into the zirconia crucible of a vacuum induction melting furnace. The heavy doors slide shut, and powerful pumps create a near-perfect vacuum state, removing all oxygen to prevent contamination. Song 2 Tron, electromagnetic fields, then shape the molecular structure of the ingot, heating it without physical contact. In a slow-motion macro shot, the superalloy liquefies completely, radiating an extreme white-hot glow at 1500 degrees Celsius. The liquid metal churns violently under the magnetic field. Suddenly, the crucible tilts, pouring a blinding, golden-orange stream of molten metal into the glowing ceramic mold. Air ripples distort the camera lens as the liquid fire settles into the intricate channels of the hot matrix. Now we reach the pinnacle of casting science, single-crystal growth.
High-speed camera.
The filled mold is slowly lowered out of the furnace heating zone into a liquid cooling pool.
Hot ceramic matrix.
At the base of the mold lies a narrow, helical, pigtail, selector. As the metal begins to freeze from the bottom up, this spiral pathway forces the metal crystals to block each other until only one single crystal grain is allowed to escape and grow upward. Over several hours, the entire blade solidifies as a single, uniform crystal structure with no internal grain boundaries. This elimination of boundaries is what prevents the metal from stretching or creeping under extreme operational stress. Once cooled, the mold is struck by a high-frequency pneumatic knockout hammer. White ceramic fragments explode outward, revealing the pristine metallic tree beneath. A 10,000 psi water jet blasts away any stubborn internal ceramic pores, leaving the high-tensile metal glistening through the violent spray. A diamond-tipped circular saw then cuts each individual blade away from the central metal runner, sending dense clusters of bright orange sparks flying into the air. The raw blade is submerged in an acid leaching bath to chemically dissolve the remaining internal core, opening up the tiny, hollow cooling passages. Look through our microscopic camera as we navigate through these smooth, internal channels deep inside the blade. The component is then placed into a vacuum heat treatment furnace, glowing cherry red to homogenize its crystalline structure before adopting a futuristic matte-grade titanium finish. A 3D coordinate measuring machine uses a ruby-tipped probe to verify the aerodynamic profile down to the nanometer. Finally, a high-power laser drilling machine fires ultra-fast pulses of light energy, punching thousands of microscopic film cooling holes along the leading edge.
The blade
is then polished to a mirror reflection, ready for inspection. In aviation, there is no room for error. Every single blade must undergo the most rigorous non-destructive testing known to science. The polished blade is carried into a lead-lined industrial X-ray computed tomography scanning chamber. The heavy shield doors slide shut with a definitive mechanical hiss. On the engineer's console, a transparent, three-dimensional X-ray view of the inner metal crystals appears. The engineer zooms deep into the structure, searching for any hairline cracks or micro-voids hidden from the human eye. Advanced AI scanning software runs a parallel analysis, highlighting the entire model in a vibrant green, past overlay. Next comes the fluorescent penetrant inspection, where the blade is dipped into a neon yellow chemical liquid. Under a pure ultraviolet black light, the blade shifts into an otherworldly fluorescent green. Any surface micro crack would hold onto the die and glow brightly. But this blade is flawless. It is now transferred to the thermal barrier coating zone. Here, an automated plasma gun fires a 10,000-degree electric arc, vaporizing and spraying a cream-colored layer of yttria-stabilized zirconia gum onto the airfoil. This micro-layer of ceramic acts as a heat shield, allowing the blade to operate in gas temperatures that actually exceed the melting point of the metal itself. The finished blade lies elegantly on a black velvet platter, a 20-centimeter piece of engineering that can withstand a centrifugal pull equivalent to the weight of a commercial cargo truck. A unique serial number is laser-etched onto the root, and the components are sealed into climate-controlled flight transport cases, ready to be integrated into the propulsion system. The final assembly takes place in a sterile hangar, where aerospace technicians manually interlock individual turbine blades into a massive central rotor disc. The complex, fir tree, roots slip into the disc slots with zero clearance, creating a circular metallic fan of geometric perfection. This completed core turbine section is lowered by a heavy crane into a reinforced ground testing cell. The jet engine ignites with a deafening roar, firing a ferocious, screaming supersonic blue exhaust flame into the bay. Inside the engine, the very blades we watched being poured from liquid fire are now spinning at 15,000 revolutions per minute, swimming in a continuous 1700-degree inferno of burning aviation fuel. We pull back to an air-to-air drone shot of a modern passenger jet climbing steeply, tearing through a thick sea of clouds into the bright sunlight. From the cockpit, the horizon opens up, powered by the invisible strength of the single-crystal blade spinning flawlessly inside the nacelle. At Inside Factory Produce, we are honored to bring you this exclusive look at the pinnacle of human manufacturing. This is where sand, wax, fire, and liquid metal converge to conquer gravity. Every flight you take relies on this unseen precision, a testament to the engineers who forge trust into every crystal lattice. Thank you for watching this industrial deep dive. Don't forget to like, subscribe, and share this video to support our journey into the world's most incredible factories. Until next time, keep your eyes on the skies. And remember, the future is not just built, it is cast in the fires of human ingenuity. Engineering trust in every single flight.